On our marble roller coaster, the height at the first drop is 50 centimeters. The loop's diameter is 19 centimeters. The distance from the top of the hill to the bottom of the loop is 76 centimeters. The mass of the marble is 0.002747 kilogram. Velocity at the bottom of the loop is 2.747 meters per second. Velocity at the top of the hill is 0.556 meters per second. The height of the second hill is 22 centimeters.
The friction force, we use the measured velocity at the bottom of the loop, which is 2.747 meters per second, and we solve for the average force of friction with the law of conservation of energy, which states potential energy initial plus kinetic energy initial plus work is equal to potential energy final plus kinetic energy final. And to find friction, we would solve for the force times distance within the work. Then we expand it out, which is equal to m mass times gravity times height plus 1/2 mass times velocity squared plus force times distance is equal to mass times gravity times height final plus 1/2 mass times velocity squared. Then we cancel the masses and we take out the potential energy final, as there is no potential energy final at the bottom of the loop. And then we plug in the numbers and solve, and we are left with 9.8 meters per second squared times 0.5 meters plus force times 0.6 meters is equal to 1/2 2.747 squared. 4.9 plus force times 0.6 divided by 0.002768 is equal to 3.773, and then we simplify it out to force times 0.6 is equal to negative 0.00312, and then after solving for force, we get the average friction force of the styrofoam tubing is negative 0.005199.
With the video gate, we measured the velocity at the top of the hill to be 0.556 meters per second. With this information, we calculated the velocity at the bottom of the hill, or at the end of the loop, using law of conservation of energy. In the equation, we can cancel out the initial potential energy due to the fact that there is no potential energy at the bottom of the hill. Therefore, we get the equation mass times velocity squared over 2 plus distance times force equals mass times gravity times final height plus mass times velocity squared divided by 2. Plugging in the measurements and performing the calculations, we get that the initial velocity, or the velocity at the bottom of the hill, will be 2.4 meters per second.
In order to solve for the speed at the top of the loop, we must use the law of conservation of energy. The first step is to cancel out potential energy initial, as there is no potential energy at the bottom of the loop. We are left with the equation kinetic energy initial plus force times distance, which is work, is equal to potential energy final plus kinetic energy final. And then we plug in our numbers. After all of your calculations, you should be left with velocity is equal to 1.68 meters per second. In order to find whether or not the marble will drop off the track during the loop, we must calculate the centripetal acceleration at the top of the loop, as that is where the velocity will be the least. In order to calculate the centripetal acceleration, the formula is centripetal acceleration is equivalent to velocity squared over radius. And substituting numbers in, we get centripetal acceleration is equal to 1.68 meters per second squared divided by 0.095 meters. And the centripetal acceleration is 29.71 meters per second squared. And since 29.71 meters per second squared is greater than the acceleration of gravity, which is 9.8 meters per second squared, the ball is able to pass through the loop without dropping.
Additionally, we calculated the normal force at the top of the hill in order to mathematically prove that the ball does not fly off the hill. Using the measured velocity and mass, and the equation that says normal force equals mass times gravity minus mass times velocity squared over the radius, we get that the normal force is approximately 0.0232 newtons. A negative normal force would mean that the marble would fly off the track. However, the result was positive, thus showing that the marble will stay on the track.
Our original plan was to have the ball start at a height of 0.8 meters. However, this gave the ball too much energy and it became airborne over the hill. After vigorous calculations, we refined our roller coaster to have a higher hill at 22 centimeters instead of 20, and a starting height of 50 centimeters to lower the centripetal force and keep the ball on the track. We tried this in real life and it was successful. In fact, the measured speed at the top of the hill, 0.556 meters per second, was only 0.14 meters per second lower than the calculated. Our main source of error was the ball not traveling perfectly down the track and constantly bumping into the sides. This caused the marble to lose some energy and thus velocity, so the measured velocities are always slightly lower than the calculated.